Welcome everyone. Today we're on Zoom and I'm Laura. I'm the PR manager of ESA-BJ, and we have today as our guest speaker Professor Athena Coustenis from the European Space Agency. She's going to CNRS actually, but she's working on the exploration on the ExoMars programs of the European Space Agency. Professor Ip, the executive director of ESA-BJ, whom you can see in the camera, he will introduce Professor Coustenis in a moment. But before that, I would like to say a couple of words about the On Things to Come series and ESA-BJ, so the International Space Science Institute Beijing. The institute was established in 2013. It was established thanks to the cooperation between the International Space Science Institute in Bern, Switzerland, which was established in 1995, and the National Space Science Center of the Chinese Academy of Sciences here in China. And together, the two institutes work to advance space science studies. So the goal is to gather scientists and experts and researchers at our premises, organize workshops and different kind of activities, forums, international teams, working groups. It really depends on the scope and on the goal of the research topic. And by inviting scientists and experts here at our premises, we try to cover different disciplines in space science studies and again contribute to the scientific community and to the advancement of research in this field. Given the current pandemic that is still ongoing, we unfortunately weren't able to organize any offline events since beginning of last year. But we've started a couple of webinar series. The current one, the present one, the On Things to Come webinar series, which focuses on ongoing and future space missions. And now we also have a Chinese webinar series, a webinar series in Chinese, which is called 1001 Space Nights, where we present the achievements and work of Chinese women scientists. So again, today we are going to talk about the ExoMars missions with Professor Coustenis. Many thanks once again for accepting our invitation. We're glad that you're here, and Professor Ip maybe can say a couple of words about her. Thank you.
Right. Thank you, Laura. And today we're very happy to be able to invite Professor Athena Coustenis to come to here to give the talk on the ExoMars mission, which is a very important one, you know, that as you were here. But first, let me say a few words about Athena herself. And she is a director of research of CNRS of France, and she's an astronomer at the Meudon Observatory. Her research specialty and interest is on planetary atmospheres, especially, I mean, she has done tremendous amount of work on Saturn and Titan in particular. I mean, she has contributed greatly to the Cassini mission, the science analysis. But now she's working on something else. You know, she's very busy, and she has a very, I would say, wide influence on the European space science and also at the international level. For instance, she's director of ESA, so Human Exploration and Robotic Research Science Advisory Committee, and then she's also the chair of the COSPA panel on planetary protection. I mean, if you want to go anywhere else, you know, other than the Earth, you have to ask her for permission. And she's also the chair of the CNES, French agency's Science Advisory Committee, SAC. And then just a minute ago, she told me that she just got a new task, which is to work to work with the NASA's decadal survey on planetary science, which is an extremely important one. But all that, you know, we could talk about her for hours. But I think that we have time limit, so I would ask Athena, please, you take it away. Thank you so much.
Thank you so much, Wing. Pleasure to be here today. And by here, I mean virtually, but it would have been really my pleasure to come to Beijing. I have had the pleasure of visiting the ESA-BJ Institute quite some time ago. So I hope one day we'll be able to meet again in person. But in the meantime, I'll take you to a trip to Mars. So let me first turn off my video so that I don't have any connection issues, and just say that as Wing said, I'm Athena Coustenis. I'm a planetologist working at Paris Observatory in Meudon, which is the image that you see here in the lower right. And as a planetologist, as Wing said, for those who know me, I'm rather specializing in the outer solar system. And on this mission, Cassini, that Wing mentioned, but that he also helped put in place quite some time ago. He's the initiator of that mission with other colleagues. But I'm interested, obviously, as a planetologist in all planets, and in particular Mars, where I have become even more engaged to following the exploration of Mars because of the different functions that Wing just mentioned in the different science advisory committees in ESA, in COSPAR, in the National Center for Space Studies in France. So let's go to Mars. And first thing to say is that Mars has always been a fascination for many people in history. The red planet is close, but still very mysterious. And it's a planet that has harbored life for some of the most important writers in the literature, including Cyrano de Bergerac, Fontenelle, Flammarion, and even Edgar Rice Burroughs, the creator of Tarzan, who wrote a series about Mars called Barsoom. And there has been a long controversy in the previous century on the subject of channels and the observations by Schiaparelli and the idea that was reprised by Percival Lowell. So there is a long history behind why Mars is so important, but also one has to realize that Mars is indeed explored also due to its proximity and also theorized habitability. Indeed, Mars is the fourth planet from the Sun, and an important object to consider when one refers to possible habitats in the solar system. In one of the most important goals in space exploration, you find humanity's search for life, which is very much connected also to our better understanding of our origins and our evolution. And the requirements for life, as you all know, as we know it on Earth, involve liquid water, essential elements, that's the nutrients, energy sources, and a stable environment. In the habitable zone, that's the blue strip that you see here, which is actually the region located at a certain distance from the sun, where it is theoretically possible for a planet with sufficient atmospheric pressure to maintain liquid water on its surface. There is our Earth in the middle. Earth is the only inhabited planet we know today. But you can see Mars right here, right at the right-hand edge. And the search for other habitable worlds actually was first restricted to our close neighborhood, and that's essentially Mars. And this is due to the fact that Mars may have been at some point conducive to life. And so Mars has been a place of high relevance and interest for exploration. And still today, the planet we have visited the most, with about 50 missions attempted since the 60s. So I wanted to give a little bit of context on Mars science and Mars exploration, and then I'll focus on the ExoMars missions. So 3.5 billion years ago, Mars, we think, had a fairly dense atmosphere and a lot of water running on the surface, and I'll say why in a minute we think that. And we think we lost it due to many different aspects like gravity, lack of magnetic field, and so on. But some of the habitable conditions exist today on Mars. And as I said, in its early history, Mars arguably looked more like Earth. And like it, most of its carbon dioxide was recycled in carbonate rocks. But without plate tectonics, Mars is unable to recycle rocks into carbon dioxide in the atmosphere, and therefore cannot maintain a strong greenhouse effect. And this is why Mars today is very cold. It's minus 60 degrees Celsius. And probably part of its atmosphere has been lost to the solar wind and radiation. But Mars still has a fine atmosphere today, composed essentially of tiny amounts, mainly of carbon dioxide, but also nitrogen, argon, as well as traces of oxygen and water. And as for the average pressure on the surface of Mars, it is only 7 millibars. So this pressure and temperature conditions do not allow for the presence of liquid water today on the surface of Mars. Water is mainly present in the form of ice, which is found condensed in the north and south poles. And in these regions, there is indeed ice water below that of CO2 that evaporates in the Martian summer and sends water vapor into the atmosphere. But the possibility of past or present life on the planet Mars remains an open question. So this is a very busy view graph, but it shows you how many missions have visited Mars. And this is a draft that stops in 2018. So you see Mars has been a strong attraction for exploration and, you know, for good cause. Many missions have gone there, but until 2018, the Mars exploration was a history with many failures. One has to realize it's a difficult task, and 50% almost of all the missions with many international stakeholders attempting it failed. You see here flybys and images of the surface that were first acquired by missions like the Russian Mars 1 to 5 or the American Mariner 4 to 9 in the 60s. The Viking missions in the 70s brought orbiters and landers with great success, followed by a long absence of exploration, except for the Phobos orbiter, until the mid-90s with Mars Pathfinder and Mars Global Surveyor. The early years of the 21st century marked the arrival of Mars Odyssey, followed by ESA's Mars Express and NASA's rovers in 2003, and Mars Reconnaissance Orbiter and the Phoenix missions. And in the past decade, the exploration has accelerated with more successes like MSL and MAVEN, but also ExoMars TGO and INSIGHT. So just to remind everybody about the hopes and disillusions of the first missions, here's the Viking mission that had 2 orbiters and 2 landers. And aboard the landers was an experiment package for detecting biological activity that gave a negative answer, absence of organic molecules. And so in spite of the Viking success, the NASA Mars program was interrupted for 20 years. Meanwhile, on Earth in 1996, David McKay and colleagues announced that they had identified organic compounds in a Martian meteorite. That's what you see here in the bottom left. And in addition, the author suggested that these compounds, in conjunction with other clues of a mineralogical nature observed in the rock, could be evidence of ancient Martian microorganisms. And these results, which are still, I have to say, controversial today, nevertheless made it possible to resume exploration of Mars with Mars Pathfinder, which landed successfully on July 4th, 1997. And it was the precursor of a long series of missions involving rovers and orbiters. And you can see here some of the images and the data that has been recorded and returned to Earth by various spacecraft. And they concern the atmosphere, the surface, and you also see here the recent INSIGHT mission, which showed some indication of seismic activity. But the main search on Mars is obviously for past or current water. And you see here how the different missions have brought a lot of evidence for the existence of liquid water on Mars, at least in the past. And here are some images already from Viking showing evidence for ancient valley networks and some outflow channels, but also indications of past water from more recent missions with surface features here from Omega Mars Express, so the discovery of clays in the old terrains of Mars. And clays are formed by liquid water at some point in the early history of Mars. You can also see here measurements from MSL Curiosity. And the conclusion from these from this data is that if life existed on Mars in the past, it must be searched for in the first giga here in the early history. And this is compounded today by other measurements, but also we have from observations by the gamma ray spectroscopy experiment on Mars Odyssey and the Mars Global Surveyor, measured with the radar, also on Mars Express and MRO, that water is present under the surface. And you can see here the famous polar ice caps on Mars. So this is an artistic image and a concept that shows the early Martian environment to the right, believed to contain liquid water and a thicker atmosphere, versus what we have today, the frigid, inhospitable environment on the left. But as we saw just now, Mars has features like dry riverbeds and minerals that only form with liquid water and indicate that long ago it had a thick atmosphere that retained enough heat for liquid water to flow on the surface. And hence, perhaps some people hypothesize that it may have witnessed the emergence of life. And it appears that Mars has lost much of its oceans and its atmosphere over billions of years, transforming its climate from one that might have supported life into the desiccated and frozen environment we see today. And all of this comes from results from missions such as ESA's Mars Express, that I'll talk about in a minute, also the ExoMars TGO, and NASA's Maven and Curiosity, and as I said, going back all the way to the Viking missions in 1976. So indeed, besides the surface, thanks to such measurements I just mentioned, we also have a better idea of the evolution of the Martian atmosphere and the loss to space of its constituents over the years. And this is not an easy task to do. The problem is that measurements of the 018 over 016 isotopic ratio on Mars have not been consistent, and we get different measurements from different missions, which results, you know, for us in a different understanding of the ancient Mars atmosphere. But recent measurements of the argon isotopes on the Maven mission has allowed for an estimation of how much atmosphere Mars lost to space. And they also determined that the majority of the planet's CO2 was also lost to space by sputtering. And CO2 obviously is interesting because it is the major constituent of Mars' atmosphere, but also because it's an efficient greenhouse gas that can retain heat and warm the planet. So by these measurements, it was determined that solar wind and radiation are responsible for stripping the Martian atmosphere, transforming Mars from a planet that could have supported life billions of years ago into a frigid desert world today. However, even if we understand some things a little better today, the mystery remains. We know Mars had more atmosphere. We know it had flowing water, but we do not have a good estimate for the conditions apart from that. How Earth-like was the Mars environment? For how long? Could traces of life be found there? Are there credible signs of possible life? So a lot of effort is devoted to the planet's exploration to answer these questions. And Mars is still the place that can teach us a lot about where we come from and how life could emerge and be sustained on our own planet and elsewhere. And you can see here, for instance, an image from Mars Express with the confirmation of the polar Martian Ocean. So the family of missions to Mars has grown even more recently, with more missions now in place since just this past year, bringing it up to something close to 50 missions by 9 different nations since the 60s. And all of these missions search for signs of extant or extinct life on Mars. But the next steps will be dedicated to going deeper, doing a more thorough exploration, and eventually bringing back pieces of Mars to Earth. With such goals, 3 new spacecraft were launched and arrived at Mars just these past couple of months, and are highlighted here on the right with the yellow ovals. So indeed, demonstrating the unabating interest for the red planet. Many more missions are ongoing or in the works. And very recently, you can see here in the summer of 2020, and within a few days, one from another, several countries launched missions: the United Arab Emirates, NASA, and China. And they all arrived this February, just in February 2021, to complete the current fleet of missions around or on Mars, bringing it up to 11 missions in operation on site. And you have here the up right, the United Arab Emirates' first interplanetary HOPE probe, Al-Amal, which is orbiting Mars to study its atmosphere and climate, among other, looking for connections between today's Martian weather and the ancient climate of the red planet. You have China's Tianwen-1, fantastic Mars mission, which consists of an orbiter, a deployable camera, a lander, and a rover, and will access the planet's environment while also searching for evidence of both current and past life. And finally, you also have the NASA Mars 2020 mission with the Perseverance rover, which will study the Martian surface at Jezero crater and will drill and collect core samples of Martian rock and soil, then store them in sealed tubes for pickup by a future mission that would ferry them back to Earth for detailed analysis. And I can't fail to say congratulations to all our Chinese colleagues for the fantastic achievement of China sending a robotic spacecraft to Mars, that's Tianwen-1, which consisted, as I said before, of the orbiter, the camera, the lander, and the Zhurong rover. I understand Zhurong is a god for fire, and this spacecraft is on fire with a total mass of nearly 5 tons, and it's one of the heaviest probes launched to Mars, and it carries 13 scientific instruments. So after placing in orbit and then successfully landing on Mars just a few days ago, then on May 19, 2021, they deployed Mars rover Zhurong, transmitted its first colored images. For those who know NASA Spirit rover, visually and technically, Zhurong is very similar to that. And what you see down here on the left side is the front view that shows the landscape of Utopia Planitia. And I understand you'll hear more about Tianwen. I just wanted to share this video with you for this mission that really is a highly successful mission. So very successful mission. Again, congratulations. You saw that there are 13 scientific instruments there on board. Another very successful mission here, the Mars 2020 mission of NASA with the Perseverance rover and strong international collaboration, which has 4 main scientific objectives now, Perseverance. It's going to do geological measurements to study the rocks and landscape at its landing site, which is Jezero crater, astrobiological measurements to determine whether an area of interest was suitable for life, sample caching, find and collect promising samples of Mars, rock and soil to bring back to Earth in the future, and also prepare for human exploration in the next decade or so, or further. And here I'm showing the on the right side at the bottom, the Ingenuity flight that took place in the Jezero crater, as I said before. And you see here on the left the 7 primary instruments on board of Perseverance with an advanced camera system. You also have sensors to provide measurements of temperature, that's MEDA. Also MOXIE, an exploration technology investigation to produce oxygen from Martian atmospheric carbon dioxide. You have the planetary instrument for X-ray, PIXL. You also have a ground penetrating radar to provide centimeter scale resolution of the geologic structure of the surface, RIMFAX, and also Sherlock, a spectrometer to provide fine scale imaging, and also using an ultraviolet laser to determine fine scale mineralogy. And finally, last but not least, SuperCam, which is an instrument that can provide imaging, chemical composition analysis, and mineralogy. And the instrument can detect the presence of organic compounds in rocks and regolith from a distance. And this instrument has significant contribution from the CNES in France, and actually also from my laboratory, Lesia, in France. So very nice mission also that is working with the cameras I just mentioned. And here you see the Jezero crater, which is the landing site. And here is where we're taking the first images with Perseverance. And one of the important things here is also to note that this is a huge achievement, because this crater is of amazing importance for future measurements. In particular, because if I turn now to the European Science and Technology exploration of the Red Planet, we have one amazing mission here. I'd like to mention the Mars Express orbiter, which is in place since 2003 and at least until 2022. And it images the Martian surface at high resolution, 10 meters per pixel approximately, and even higher resolution at some areas, and produces a map of the mineral composition of the surface. It also maps the composition of the atmosphere, and it determines the global circulation. It looks at the structure of the subsurface to a depth of a few kilometers. It determines the effect of the atmosphere on the surface, and it evaluates the interaction of the atmosphere with the solar wind. And among recent results, I just wanted to mention that the first radar sounder is on MEX ever to orbit another planet, and has detected subsurface layers of water ice, as you saw before. And another instrument has detected enough water in the polar caps to create a global ocean 11 meters deep, and revealed vast plains of permafrost around the South Pole. You see here all the mission highlights of this mission that actually also detected clouds made of water ice around Mars at an altitude of about 80 kilometers. And in an endeavor to discover why the atmosphere is so thin and dry today, Mars Express has studied the upper atmosphere and ionosphere, detecting hydrogen and oxygen ions escaping into space. So we get new insights into the structure of the ionosphere that included the discovery of a new meteoritic layer created by fast-moving cosmic dust. So all of these achievements by Mars Express help us get a better global picture of what is going on Mars. And one of the things also that Mars is doing is a flight over Jezero crater that I just mentioned. And so you can see here how it surveyed the landing site of NASA's Perseverance, the Jezero crater, which is located in the Syrtis Major Quadrangle. It's a crater with a diameter of about 50 kilometers or 30 miles. And it's very interesting, the Jezero crater, because in 2015, I believe, some researchers from Brown University described how an ancient Martian lake system existed in Jezero. So this is a crater. You see here the round ellipse where Perseverance landed. And so it had a lake in the past when the valley networks were forming on Mars. And the study also advanced the idea that water filled the crater at least 2 separate times, because there are 2 channels on the northern and western sides of the crater that probably supplied it with water. And each of these channels has a delta-like deposit where sediment was carried by water and was deposited in the lake. And clay minerals, as you know, have been detected in and around the crater, and that means that there was water once and maybe life in ancient times. So it's important to understand that this quest continues now with the new ESA exploration program that is called the European Exploration Envelope Program. So in addition to the ISS continuation, and that's what we call Cornerstone 1, reaching beyond low Earth orbit for human presence in Cornerstone 2, robotic moon with landers in Cornerstone 3, and the robotic Mars exploration follows in Cornerstone 4, which is a very important item in the ESA project because obviously of interest for the red planet. And you have also here indication of 2 transversal activities in ESA, the expert and the science-based elements to support future mission developments. This is what is shown here, the roadmap to Mars exploration via the moon. So ESA is accelerating the exploration of the moon and Mars. And this slide illustrates a roadmap and timeline for moon and Mars exploration leading to Mars sample return, which I'll discuss in a minute, and eventually human exploration. And each of these destinations that you see here provides unique opportunities for contributing to a broader understanding of different topics like fundamental laws of the universe, all the way to the history and extent of life in our solar system. So this is ESA's program that is also focusing on the ExoMars missions. ExoMars comes from exobiology on Mars. So this is an astrobiology program initially by the European Space Agency and also the Russian Space Agency, Roscosmos. And since its inception, actually, ExoMars has gone through several phases of planning with various proposals for landers, orbiters, launch vehicles, and international cooperation planning. And I remember in particular from 2009 until 2012, there was the Mars Exploration Joint Initiative, which was studied as a collaboration between ESA and NASA for 2 rovers being delivered at once jointly, and they would explore Mars together. But this was canceled due to budgetary restrictions in ESA, and the whole project had to be reconfigured. And in 2013, Roscosmos became the new partner and joined ESA in the ExoMars project. Roscosmos collected 2 instruments aboard TGO in the process, but it contributed also 2 Proton launch vehicles. And the goals of the ExoMars missions are to search for signs for past life on Mars, investigate how the Martian water and geochemical environment varies, investigate atmospheric trace gases and their sources, and by doing so, demonstrate the technologies for a future Mars sample return mission. And you see here the ExoMars program, which comprises 2 missions. The first one is the Trace Gas Orbiter, which launched in 2016, while the second one, which is the rover and the surface platform, is planned now for 2022, following what I said, the reconfiguration of this mission. And together they will address the question of whether life has ever existed on Mars, as do the other missions. And so you see here the Trace Gas Orbiter, which I'll call TGO from now on. The first mission also involved a test stationary lander called Schiaparelli, and they were launched on 14 March 2016. TGO entered Mars orbit on 19 October 2016 and started its effective mission in December 2017 and will work until at least 2022, serving as a relay for Mars 2020 and the ExoMars 2022 rover. Since orbit insertion, TGO proceeded to map the sources of methane and other biological and trace gases present in the Martian atmosphere that could be evidence for biological or geological activity. And in 2017, it started its effective mission. It studies, as I said, the Martian atmosphere, and it started actually aerobraking, which ended in March 2018. The Schiaparelli experimental lander separated from TGO on a descent to Mars and was maneuvered to land in Meridiani Planum, but unfortunately crashed on the surface of Mars because of a software problem that we all hope has been solved for future missions. So here are the TGO instruments. It has 4 main instruments. And as I said, it will also act as a communications relayed satellite. You have ACS and NOMAD comprising 3 spectrometers each and covering complementary wavelengths. They are charged with taking a detailed inventory of Mars atmospheric trace gases and will monitor seasonal changes in the atmospheric composition and temperature in order to create a detailed atmospheric model. So the instruments also have the capability to detect minor atmospheric constituents that may exist, but have not yet been detected. To complement these measurements, CASIS will image and characterize features of the Martian surface that may be related to trace gas sources such as volcanoes. And meanwhile, FRIEND maps subsurface hydrogen to a depth of 1 meter to reveal deposits of water ice hidden just below the surface, which, along with locations identified as sources of the trace gases, could influence the choice of landing sites for future missions. So this is the payload, and some of the first results from TGO were published 2 years ago. There was new evidence of the impact of recent planet-encompassing dust storm on water in the atmosphere, and that was done with NOMAD and ACS on the one hand, and FRIEND on the other. And those are the scientific highlights that were published at the time, along with surprising lack of methane by ACS and NOMAD. And the reason I say that this was surprising was because at the same time as the rover Curiosity, the Mars Express instruments had announced the detection of methane in the Martian atmosphere, which is surprising in itself because the atmosphere of Mars is oxidizing with CO2, as I said before. So some wondered if this was a possible clue to a form of life, because on Earth, methane is 90% bound to life. It is in fact a byproduct of the metabolism of living organisms. But more recently, ExoMars' orbiter, the trace gas orbiter, as I said, has not confirmed the presence of methane in the upper atmosphere. So it seems that methane on Mars is very close to the ground and remains actually to be confirmed and explained for its vertical distribution. But it could be linked to volcanic or hydrothermal activity, and its non-detection by TGO could be explained by a heterogeneous chemistry that destroys it in the upper layers. But it's also necessary to point out the difficulty of interpretation of the measurements made by the various instruments in the presence of other atmospheric gases. So the question of methane on Mars remains. I just wanted to mention briefly some other recent results from the ExoMars TGO team. Just in this February 2021 in Science Advances, were published the results that unveil an entirely new class of chemistry and provide further insights into seasonal changes and surface atmosphere interactions as driving forces behind the new observations. And here is the discovery of hydrogen chloride with TGO-ASS which points to a very heterogeneous chemistry on Mars, not well understood, but could be indication of magmatic activity. Also here, they're new, along with the new gases I just mentioned, TGO is refining our understanding of how Mars lost its water. So it's a process which is also linked to seasonal changes. And here is a result from the NOMAD instrument that points to the identification of a highly variable D2H ratio throughout the atmosphere, and an indication of loss of water from the atmosphere. Recent science results, here you have FRIEND results confirming the ODYSSEY measurements for subsurface hydrogen, indicated water in different forms, absorbed hydrated minerals and water ice on different locations on Mars. Oh, and these are some beautiful Cassis images with giant dust devils crossing a crater floor in Mars' southern hemisphere, moving in slow and fast motion. And it's important to say that both Mars Express and ExoMars TGO have been working together to enhance our understanding of Mars. And besides confirming the existence of an ocean near the poles and elsewhere in ancient times, they have shown the first detection of vertically resolved profiles of CO, and they have characterized the distribution of ozone using infrared wavelengths and many more. So I invite you to go look at the different papers that combine observations from different missions. Just to highlight that we recently had a chance to celebrate the 20,000th image of Mars by the Cassis stereo camera taken in December 2020, where you see here features in Solis dorsum, which is a segment of a prominent wrinkle ridge system in the Tharsis volcanic plateau. So moving to the rover now, after planning for launch in 2020, along with the other missions, the ExoMars rover, as I said before, had to wait for another 2 years because a launch to Mars window opens every 2 years, as you know. And this was due to issues with COVID, obviously, but also reconfiguring the mission, finding stronger, capable parachutes, and optimizing some other elements regarding the electric thermal system and more. So here you see the ExoMars 2022 mission, which will launch in September 2022. And in 2023, the mission will deliver 2 science elements to the Martian surface, a lander instrumented to conduct environment and geophysical measurements named Kazajok, and a 310 kilogram rover tasked with conducting a search for signs of life. And this was named after Rosalind Franklin. So after landing, the rover will egress from the platform to start its science mission. The primary objective is to land the rover at a site with high potential for finding well-preserved organic material, particularly from the very early history of the planet, as I said before. And an ancient site on Mars that hosted an abundance of water in the planet's early history has been recommended as the landing site for the 2022 ExoMars to complement the measurements done by Mars 2020 at Jezero. And this is Oxia Planum, which presents advantages both for science requirements and also satisfies engineering constraints. So you see here, Oxia Planum is a 200-kilometer wide clay-bearing plain located on the planet, located on Mars inside the Oxia Palus quadrangle in the eastern border of Chryse Planitia. You can see here. The plain lies between the Morth Valley's outflow channel to the northeast and the Ares Valley's outflow channel to the southwest. And it met the rover landing criteria based on its latitude, elevation, surface slopes, very kind slopes, and its Noachian aged terrains. And it was chosen because of its relatively smooth topography and its abundance of hydrated minerals. And so here you have the science objectives of ExoMars and the payload. The science objectives are, of course, to travel back in time and explore the bottom of the Mars ocean by drilling down to 2 meters, looking for traces of life, study the surface geology and environment, and look for landing sites. And you have here the payload, which includes panoramic instruments, wide angle and high resolution cameras, a subsurface drill to acquire samples, and contact instruments for studying rocks, a sample preparation and distribution system, and the analytical laboratory, including a visual and infrared imaging spectrometer, a Raman spectrometer, a laser desorption, thermal volatilization, derivation, gas chromatograph, mass spectrometer, and more. And so the rover will establish the physical and chemical properties of Martian samples, mainly from the subsurface. And they are more likely to include biomarkers, since the tenuous Martian atmosphere offers little protection from radiation and photochemistry at the surface. The drill is designed to extract samples from various depths down to, as I said, a maximum of 10 meters. And such depth range has never been probed on Mars before. ExoMars' subsurface sampling capability will provide the best chance yet to access and analyze sedimentary deposits, possibly containing molecular biosignatures that may have been shielded from the radiation on the surface. And it includes, like I said, an infrared spectrometer to characterize the mineralogy in the borehole. And once collected, the sample is delivered to the rover's analytical laboratory, which will perform mineralogical and chemistry determination investigations. And of special interest, obviously, is the identification of organic substances. The rover is expected to travel several kilometers during its mission. It has also technology objectives besides the science objectives that I mentioned before to demonstrate surface mobility, access the subsurface, and do sample acquisition. And here is Oxia planum, which after many considerations on entry, descent, and landing, habitats, and chemotrophic organisms, looking at all these terrains, organic and biosignature best candidate was selected for the landing. And you can see here some images of the Oxia planum, which contains one of the largest exposures of clay-bearing rocks on Mars. The age of the region was calculated to be from 3.6 billion years old to 4 billion years old. And the site is iron magnesium rich clays, indicating that water once played a role there, just like for Jezero. The site sits in an area of valley systems with the exposed rocks exhibiting different compositions, a variety of deposition and wetting environments. So there are also some dark-toned erosion-resistant areas that you see. They are hypothesized to have occurred from either fluvial deposits or by volcanic activity during the Amazonian period. And there are also some erosion that has taken place here. So beautiful landing site again for the Rosalind Franklin rover. And just some images of the rover so that you know that work is occurring as we speak. Here, the landing module at Lavochkin, the spacecraft composite structural model here with some people around it, just so you can see the size. And the drawer that I mentioned, the ALD in preparation in Italy, Thales Alenia Space, and also in Airbus facilities. So this all goes towards the Mars further exploration with the Mars sample return mission that you see here, which is an exciting and ambitious project based on substantial international collaboration, in particular between ESA and NASA, to bring back to Earth some samples. You see here the Mars 2020 rover, which is responsible for sample selection, acquisition, and caching. You see the sample retrieval lander, which would deliver to Mars the sample fetch rover to retrieve the samples, then a sample transfer arm to load the samples into a container, and the Mars ascent vehicle to launch the container into Mars orbit, where it would be captured by the Earth return orbiter to deliver them to Earth by the Earth entry vehicle. So this will end with the Mars return sample handling facilities on Earth. It's very important to notice, as Wing said before, that we look very closely to planetary protection elements, both to not contaminate Mars and also to take care of the samples that will be brought back. You can see here the different elements of the MSR project that I mentioned before. And for this campaign, the rover that will acquire the samples is going to work with 42 sample canisters, from which 31 will be selected for return to Earth. So we'll get about half to 1 kilogram of material returned to the facilities on the ground. And all of this is working very well. This is an ambitious decade for Mars exploration in ESA. And I just mentioned the planetary protection elements that are of importance there, to conduct scientific investigations without harming the environment that we're investigating and bring elements back to Earth. So I'll finish with just saying that there are other missions going to Mars, like MMX, for which the COSPAR panel on planetary protection that I chair has issued a specific unrestricted Earth return, because it brings back samples from Phobos that are not of risk to our planet. And we have special requirements and guidelines for all of that that you can find on the COSPAR's policy website. And this is my last slide to say that there are big questions that remain, and we need to protect our planet, but also explore Mars safely, and other elements of habitable worlds in the solar system exist. So I'll stop there, just say how important it is to combine robotic missions and different sources. And I thank you for your attention.
Many thanks.
Yeah, thank you, Athena. And thank you for this very clear and comprehensive talk on the ESA program, and also everybody else. Any questions to Athena?
So here, for the ones in this chat, you can always write your question in the chat box, and then I will read it out loud. There is also the possibility, if you want, to unmute yourself and interact with Professor Coustenis if you want to ask the question, but that is up to you. I'm copying and pasting some questions. The first one is, thanks for the excellent lecture. And since you are a great promoter of international cooperation, when do you think we will have a joint Mars mission from China and Europe?
Very soon, I hope, is the answer. On the ESA side, I know that ESA is working very closely with China. In particular, on the science program of ESA, there's the SMILE mission that is going to look at some magnetospheric and solar observations in the solar system. And also in the exploration program, I know that we're working very closely also with China on many of these different aspects concerning the moon, and also concerning Mars, but also the space station on which ESA has collaborated on the International Space Station for quite some time. And now China has its own projects, and we are all looking very much forward to working with China on all of these elements.
Thank you very much. We indeed had actually a talk on the SMILE mission last year in November. It was given by Professor Wang Shi. Yeah. Second question, what are the requirements of planetary protection for lander missions to Mars, since there might be life there? And the same question applies to Mars sample return missions.
Yes, thank you for the question. I didn't have time to go into detail for the planetary protection issues, but Mars is actually in a very important category within the guidelines from planetary protection. So it's in category 4 as concerns landers and potential orbiter missions. It concerns a body with chemical evolution and origin that has interest and significance for also life. So first of all, you have to be careful that there are 3 subcategories that depend on the instruments you have on board, the science investigations, and the special regions where you go on Mars. Because obviously, if you go in a region where you have more chances of finding water, then the requirements are more restrictive. For return to Earth, anything that comes back from Mars is in category 5. That's a restricted Earth return, which means that when you come back to Earth, the samples have to go through special treatment. They have to go through quarantine before they're distributed to scientists, and the requirements involve both sterilization of the spacecraft and a formal reporting on any organics you may carry on board when you go out. And then when you come back, you have to say exactly what you're bringing back and take it to a special facility for treatment before it goes to the scientists.
So are there other questions can you see that, Athena?
No, I'm sorry. I'm sharing my screen.
Okay.
Maybe I should stop.
All right, I read it out for you. It says that if microbial life is found on Mars, what would be your recommendation for further exploratory activity?
First of all, we've all gone through the pandemic this past year, so we know we have to be very careful with any microorganisms or microbial life that we bring back. I have colleagues of mine, obviously I'm not a biologist, but I have colleagues of mine who have put together a very specified protocols, what you do with anything you bring back from Mars. Before you can identify and even say it's a microbial life, it will go through a lot of treatment. Then if you identify microbial life, then I suggest you put everybody in quarantine and you wait for quite some time to see what are the effects before you distribute it around the Earth. Now, there's one important, very important question here, and this is where will the samples go and who are the people who are going to work on them? So right now, within the Mars Sample Return Program, ESA and NASA and all the international partners are working on putting together teams that are specialized on identifying anything that comes back from Mars. And it's not only microorganisms and microbial organisms. It's also important in the samples, as I said before, to look at the ancient history, see what's going on with the climate. So we'll have atmosphericists and geologists and so on. So there will be a lot of specialized teams by 2030, 2031, when the samples will be coming back, we think, to look at all of that.
Okay, great. Oh, you must love this question. It's asked that could there be life on Titan, even though it's much colder than Mars?
Is Leonid asking that question?
Correct. If I can ask you, first of all, Athena, great talk. Thank you very much. Very enjoyable and interesting. Now, I would like to ask you a question which might be a little bit provocative. You presented a very broad and extremely exciting overview of, I would say, expected science. That is, finding liquid water, prebiotic molecules, etc. It's absolutely exciting, no question about that. However, as we all know, science has other types of discoveries which are unexpected, and they are no less exciting. And astronomy and astrophysics is full of that. Now, if you allow for a minute for yourself to fantasize, now you presented us exciting expected science, but in your opinion, what would be most amazing and exciting thing unexpected in the area of your expertise and, well, in planetary science and Mars in particular?
So I think, somebody mentioned Titan. If it wasn't you, Leonid and I and we go back a long way for Titan. So we're all in the Titan corner.
That's correct.
And you saw my last slide. I couldn't prevent myself from talking about other habitats, okay? Because Mars obviously has attracted a lot of attention, and you know, we've been exploring it with 50 missions, and on Titan we've had basically one essential mission, which is the Huygens mission that landed there, and the Cassini orbiter that went around. So you're asking me what would be the most exciting thing for me, and if we found even a micro minuscule organism on Titan or on Mars, would be an exciting, discovery, because I don't know that it would be similar to what we have on our Earth. So if it gave us an opening of mind on a different kind, of life form, on Titan, it's been hypothesized with methane or hydrogen or other kinds of energy suppliers. On Mars, it could be something completely different. But anything we would find is, I think, exciting beyond measure for our understanding of astrobiological potential in the solar system. And so there's Mars, and there's the icy moons. And I didn't mention it, but obviously the icy moons with liquid water underneath the surfaces open a completely, broader sense of habitable environments. So all of this is just very exciting, Leonid, and we need a new mission. I mentioned Dragonfly before for Titan, but all the new missions to Mars now and to the outer solar system include instruments that will help us go deeper, as I said at the beginning, and do a more thorough analysis.
Mm-hmm.
Great.
Okay.
Thank you very much.
Any other questions? Okay, I think this final question, because you mentioned that there are water, on Mars. Now the pool water found filling, covering the whole Mars by how much? 10 meters or 11 meters?
The poles, 11 meters, probably, but it's water ice that evaporates, occasionally. So, yeah.
So the question is that could asteroids and comets have contributed to the Martian water?
Yes.
And to what
yes.
proportion,
Yeah, absolutely. I don't think we know the exact proportion, but that's a very good question, because we know that Earth, we had a lot of meteoritic and cometary input on Earth, which actually brought at least some of the organic compounds that we see today, and it was conducive to life. And on Mars, obviously, it's going to be very similar. And as I mentioned before, Mars Express detected a meteoritic origin cloud around Mars. So you have demonstration that these things happen. I don't know the exact proportion on Mars. It's one of the things that we're studying in the atmosphere today. There's a lot of work done to help with the dust storms. As Perseverance landed and other instruments arrived on Mars, there's this huge dust storms there that people managed to study and get some results out of. But I'm hoping when the weather is settled, we'll be able to find out more about this meteoritic input.
Okay, thank you so much, Athena. I mean, any other questions? Yeah, for Athena. I mean,
from my side, haven't received any other question. And here in this chat, if anyone else has a question, can raise a hand or write it directly in the chat box. In the meanwhile, waiting for any eventual last question, I would like to thank Professor Coustenis once again for the outstanding talk. We've recorded it and it will be online tomorrow or on Friday, as usual. And we will have, as Professor Ip mentioned, another talk about the Tianwen-1 mission in September. So the Chinese Mars mission. And next week, we will also have a Chinese guest speaker, Professor Yuan Weimin, who will talk about the Einstein probe of the Chinese Academy of Sciences, which is an X-ray observatory, a space X-ray observatory designed to perform sensitive monitoring of the sky. The time is the same, so it's going to be on Wednesday, 4 p.m. Beijing time, 10 a.m. in Europe. And I see no other questions, so sorry. I would like to thank you once again and wish you a good day and a good evening for the ones on this side of the world.
So Athena, thank you so much.
Thank you very much for giving this opportunity. And as you said, Einstein probe is another big collaboration we have here also in Europe.
Oh, yes.
Very exciting. Thank you. Have a great day, great evening. Bye. Bye, Leonid. Bye, Wayne. Bye, Laura.
Yeah.